Hennessy and Patterson book is like the Bible of computer architecture, and it's really dense, and there's a lot of stuff in there. This Kaminsky book is a different kind of textbook. It's more focused on parallel computing as opposed to computer architecture. So it's a nice complement, and it reads differently than the Hennessy and Patterson stuff. So I haven't made any required reading assignments yet, but I probably will. There's a couple of chapters there in Kaminsky that are actually very good and worth looking at. So before we get started, let me throw this open to you all. So what's up? What's going on? Any Scrum-worthy ideas, comments? Well, let's see. Let me throw one thing out there. In that survey, they may. I haven't seen the survey. I'm assuming they're asking, do you want to come on site versus stay remote? I get email every time there's a COVID case on campus. They have to they notify people, and yesterday I got like 8 emails, and the day before that I got like 6, and the day before that I got like 5, and and so somehow in the past month or so, that it seems like the number of cases has just like really gone from nothing to very active, and so I'm concerned about that, and those of you who are actually coming on campus, I'm curious about how you feel, and if do you feel safe, and are you taking care of yourself, etc. This is probably a longer discussion, but it's something to think about as you answer the survey and indicate your preferences about what you want going forward in the future.
So, are you on campus right now?
No, I'm not. I'm at home. Yeah, somebody says wear a mask. Absolutely. There's a lot of things you can do to protect yourself. Somebody says CS major courses could be mostly good remotely. Yeah, the thing is like you all miss out on having the direct interactions. But I saw this. We had these training films at the lab, when COVID first started, and we were, all working from home, and they were giving us guidance on what to do inside the building, right? And they're like, you wear a mask and you turn away from the person and you pass on either side of the halls. And one of my colleagues who's a mathematician said, this is easy for mathematicians because we actually avoid each other. We don't want to look at each other. We don't want to talk to one another, right? And I thought that was kind of hilarious. And so for a lot of you all, I mean, it may be the case that, you're fine not interacting with anybody else. I mean, that's possible. But it is part of the experience to interact and chat about the work and stuff. Yeah, good for introverts. That's right. Okay, so let's see. What do we got here? So we're going to fire up the presentations. Mr. Huber will go first, and then Mr. Cow. And so let me stop share. Mr. Huber, you can tee it up, and I'm going to time you. I think the target is 10 minutes. I'm not going to cut you off if you go long, but that's
okay.
That's the target.
Let's see. I think that should be up now. Let me get this full screen. Everybody see that?
Looks good.
Okay. Great. So I'll go ahead and start. So this presentation is about our last homework assignment, which was performance analysis of 2D matrix multiplication using 1D format and its optimizations. So the experiment we conducted was how different approaches to matrix multiplication will affect the performance, and we were examining a couple of different algorithms. One of them was C-BLAST, which is or just BLAST. I think the implementation was just in C for our purposes, and which is an expertly tuned algorithm to see whether it will perform better or worse than a simple handwritten script that we wrote that was designed to just perform this one task. And how will caching come into play, and will it be noticeable at different execution points with different problem sizes? And what we were doing was performing something called DGEM, and that stands for double general matrix multiplication. And with that, we did that using a basic format, and then also with blocking, which we'll get into in a second. So the approach here is, or roadmap, was using a benchmarking script with problem sizes going from 64 to 100. I'm sorry, 1020. I've lost my mouse here. So 24 problems at a time, and then blocking sizes of 2, 16, 32, and 64. And then we wrote basic and blocking scripts. Again, CBLAS is a separate piece of software, and compared results, and we ran everything on the Core EKL compute node.
These days,
so DGEM basic basically involved using 3 nested loops, and one was to track the C matrix, which the calculation was C plus equals C plus A times B for 3 different matrices, and then one loop held the index for the C matrix, one tracked the index for the A matrix, and one for the B matrix. And so as you can see, as we move through these matrices, we have our 18 in our C, and then as you go through, you perform the multiplications and adjust the values in the C matrix. So this is just a simple 4x4 matrix, but that was kind of the basic idea on a 64 by 64 matrix or 128 by 128, and then multiply those two and add it back to that value. So to see what the benchmarking was for how long it took for it to do that. So with the blocking, we were doing the same calculation, except that we were dividing it into block size B. So now we had, as you can see with C here now, these numbers refer to the blocks rather than the values inside of those. So within each of those, those numbers actually refer to subblocks. And what we needed to do here was assign memory to the subblocks so that we could perform these calculations more efficiently. So for instance, here C, we divided this in this simplified version into 4 subblocks. And then we would be taking A and B and dividing that into 2x2 subblocks. And then that would need to go through and calculate, but we'd need to have a different kind of nested subloop in here so that it would skip, because we need to skip from 2 and 3 back to 4, because if we see how that corresponds in the C matrix, we don't go from 0 to 1 to 2 to 3. We go from 0 to 1 to 4 to 5. And then likewise, when we're moving, we have a row tracking loop that goes from 0 to 4, and it doesn't go to 8. It goes from 0 to 4, then down to 1 to 5. So we have that's all corresponds to what you see on the bottom there, where we have n being the problem size, or actually that refers to n block. And then we have a series of multiplications that correspond and track through so that we get our values. And we can do plus equals here because we're just adding to the C matrix total. And if you can just add to that C matrix and then check that out into the memory and write that back to the C block. And because we're just doing plus equals. So, and then we are doing a mem copy operation there. So that doesn't affect the actual operations that we're looking at, but I'll talk about that in a second. So Hardware we're using here is the Core KNL compute node, and that is, we have our specs here. We have the 68 cores at 1.4 gigahertz, and our high bandwidth cache, 16 gig MCD RAM, and et cetera, et cetera. Then CBLAST is a pretty old library, originated in '79. BLAST stands for Basic Linear Algebra Subprograms. It has 3 sets of routines, which are called levels, which as you get deeper in to the types of calculations that it does, it kicks down into these more complex routines. And it's actually optimized for different types of hardware. So, for instance, when we're running it on the KNL node, it actually has specific optimizations for the type of hardware that it runs on. So it's like, it's not a generalized piece of software. It's very specific in terms of like how fast it runs. So it's generally going to beat any type of software that anybody in this class is going to write, or it's been worked on since 1979. So it's pretty fast. And then GEM, for instance, is also a prime target of optimization for BLAST. So in terms of methodology, I used a batch script on Cori to run all of our tests in the controlled queue job environment to ensure parity. We're getting, all of the, everything is apples to apples here. MFLOPs were 2 n cubed times the problem size over elapsed time, because again, when we're doing moving memory around and that kind of stuff, it's not actually a floating point operation. And we're just basically, when we're doing the block operations, we're still ultimately just doing those 3 floating point calculations, and then to get megaflops, we just reduce it by 3 decimal points. And and then I use matplotlib with a log scale on the y-axis to produce the charts to help visualize the discrepancies. So here's what the results were. And as you can see with the basic, results, they plummeted pretty much as the problem size got larger until they bottomed out pretty much at 512. I got started getting consistent results at 78,000 megaflops, and at the beginning it was very fast, but I think that has to do with it being able to cache everything and just read it, because we're using linear arrays or vectors as we're reading through, and so with it being able to do that, it can just read up the memory block and use everything repeatedly as it goes through. So it is also just a smaller amount of data, so it's able to use that to run faster, and then as it kind of goes forward and it has to store everything in memory as it's computing over and over again, it just bogs down. So for the blocked, this is what I ended up with, and this is actually the wrong graph. I don't know how that ended up in there, but the one that I had actually peaked out at 250 megaflops at its peak, and which was at 512 the problem size was at 512, and the other ones for BMMCO actually all pretty much tracked evenly, except for the one for the smallest one, which kind of just trickled down from the beginning. The other ones bounced up at 256, which I think has to do also with it being able to cache at first, but also of note is that CBLAST performed terribly on the first data set, and I think that has to do with CBLAST being a large library and it having like a lot of components to load when it first runs, and but once it gets everything kind of like up and running, then it kind of realizes its full potential and really is able to blow away any of the other anything else that's being run. So and let's see. So conclusions. are that CBLAS has a large initial startup cost, which causes it to underperform in the initial blocking test. But once it has the data cached, it's able to just read everything incredibly fast and resulting in very fast subsequent reads. And then also using 2D data in a 1D format allows the cache to read it in the fastest time. So because there's a very low miss rate, and it's able to just reuse the data, especially when it comes to blocking, because it's reading, it's just also reading sequentially in the array. So it's able to reuse that data and use the cache very efficiently. So yeah, that was pretty much what my conclusions were. So thank you. And I don't know if you have any questions for me in particular, or.
Yes, let's hold off on the questions. There's probably going to be questions about your stuff in the next presentation. Why don't you go ahead and unshare, and we'll let Mr. Cow get started on sharing. And after Mr. Cow finishes, I'm going to jump in and present some additional stuff about homework 2. And then when I get through that material, then we can pause and discuss about homework 2. But if you do have questions about Mr. Huber's stuff in particular, make note of it, and we'll come back to it in a little bit.
Okay, can everyone see my screen?
Yes.
Okay. Hi, my name is Benjamin Gao, and this presentation is on last homework 2, and it's about the performance analysis and optimization of a serial implementation of 2D matrix multiplication. So the problem. The objective of this assignment was to compare the performance of matrix multiply for 3 different matrix multiply implementations. Those were basic matrix multiply, which had no optimizations done, block matrix multiply copy optimization, which was a blocking optimization, and CBLAS matrix multiply, which is a highly optimized vendor, and it's a library which Chris beforehand explained very well. So now for the approach. A brief overview of my approach was to implement these 2 different matrix multiply functions, basic and blocking, because we were given the CBLAS implementation. We ran these implementations over a set of several problem sizes, and for block matrix multiply, we ran those problem sizes over a set of block sizes as well. And we compared these results to CBLAS's performance too. So now to go into more detail of the implementation, here is the code for my basic matrix multiply. It's just like the lecture slides. It's a triply nested loop with the formula that was given. There is a slight difference, which I explain here. The main difference is this implementation uses column major memory access instead of the one in the lecture slides, which uses row major memory access. And this is because here in the CBLAS function that the professor provided us has CBLAS column major, which was important to note because our matrix implementation, we're using a 1D vector as a pseudo matrix. So the way we access the indices, the order in which we access the indices matters, which is why here you can see usually these 2 indexes would be switched, but since it's column major, I had to switch it. So now I'm traveling column-wise in matrix A and row-wise in matrix B. Okay, now for the implementation of blocked matrix multiply. So the main idea of blocked matrix multiply is to split the n by n matrix into n by b blocks. Each block is a smaller b by b matrix, and in this blocked matrix multiplication, you would add a copy and write for blocking into cache. And here's the code. So I just put in pseudocode for the main implementation, which is similar to the lecture slides again. And here I put what I used for copying blocks A and B into cache. I didn't use memcopy like Chris did. I'm not very familiar with memcopy, but I used 2 for loops instead. And as you can see here, once again, since CBOS was using column major memory access, we had to use column major blocking as well. And the reason why we're blocking is to decrease the number of memory accesses that we need to do, decrease the amount of cache misses. And this is similar to homework 1 with structured memory access, where with the -03 optimization, we could minimize the amount of memory accesses we needed. And the main reason for this is because flops are free for modern processors, like the professor said in a previous lecture. So if we decrease the number of memory accesses and increase the number of cache accesses or cache hits, then we can significantly increase our performance. Now for the evaluation, here were the machines that I was running on. So I ran the tests on both Cori and on the virtual machine. So as you can see here, this is the specs of my laptop that I ran these tests on, and everyone knows what Cori's specs are. So some more details on what and how we're testing. So I tested basic, blocked, and CBOS on both machines. I ran experiments on these problem sizes, and for blocked matrix multiply, I ran each problem size over these block sizes. And the performance metrics that I used was the elapsed time of matrix multiply using chronotimer. So the instrumentation code was surrounding just the matrix multiply functions. And I calculated megaflops per second as the main performance metrics for analysis. So now for the results. Here is the basic matrix multiply versus CBOS matrix multiply as data. Here's the VM and Cori. Of course, this is nothing, you can't really see much, so I'll go to the table. As you can see, basic matrix multiply does a little bit better than CBOS for small problem sizes, but once the problem sizes get much larger, CBOS blows the basic matrix multiply out of the water, and this occurs on both machines. And now for block matrix multiply versus CBOS, once again, here are all the tables, but this is just a lot of data that isn't very useful right now. So here are the table or the charts for these tables. So as you can see, my results were very consistent for blocked matrix multiply, especially on Cori, where they were basically straight lines. And then blocked matrix multiply with the size of 2 ran a lot slower than CBOS, which I will get to of why I think that happened in the next couple of slides. So my analysis, performance of basic matrix multiply was better than blocked matrix multiply for a block size of 2. So if I go back to the data here, basic matrix multiply reached about 1,700 megaflops consistently, but for block size of 2, you can see that it didn't even reach the thousands for megaflops per second. And the reason, my hypothesis for this was because the copying and extra writing adversely affected performance, mainly because basic matrix multiply is just block matrix multiply, but with a block size of 1, but you aren't doing any copying or extra writing. And so you aren't really getting the effects of blocking with such a small block size. And some more evidence for this is when I had a very large block size of 64 for a problem size of 64, block matrix multiply still performs slightly worse than basic matrix multiply, which you can see here. So basic matrix multiply hit about 4,000 megaflops per second, and block matrix multiply for 64 hit about 3,500 megaflops per second. So the reason I think this is because the copying and the extra writing increase the runtime. But some other observations that I saw were basic matrix multiply and block matrix multiply. The performance across all tests were very consistent. The only inconsistency that I saw was basic matrix multiply on my VM for problem sizes 64 and 128. There was a much larger dip from 64 to 128, as you can see here. And then after, with larger problem sizes, it mellowed out. And the reason I think this occurred was because of caching. Since our biggest block size was 64, this probably also meant that our cache could hold the block size of 64 easily, which meant that for basic matrix multiply, the problem size of 64 meant it could hold everything. And then some more analysis. CBLOS performed worse for smaller problem sizes, and CBLOS performed drastically better for larger problem sizes. So I had two hypotheses for this. One of them came from because my algorithms teacher said that for Java arrays.sort, usually when you give an array, it uses either merge sort or quick sort or some combination of the two. But if you give a really small array, Java arrays.sort doesn't use merge sort or quick sort. It just uses basic selection sort or insertion sort because it determines that it doesn't need to do any optimizations because runtime or performance wouldn't really matter for such a small problem size. But unfortunately, with this hypothesis, the data doesn't really support this because, as you can see here, especially on Cori, if that hypothesis was true, the problem size of 64 wouldn't be so low in megaflops per second. It would be more equal. But since that wasn't the case, another hypothesis I had was that CBLOS optimizations adversely affect performance at smaller problem sizes. And evidence for this was with the blocked matrix multiply, what I explained earlier, where a blocked matrix multiply of block size 64 performed worse at problem size 64 than basic matrix multiply at problem size 64. And the reason I think was because of all the extra optimizations that had to do before actually running the matrix multiply. So I think because CBLOS has all these optimizations, it goes through a lot more before it starts the actual process of matrix multiply, which hurts performance for small problem sizes, but in the long run, it makes it a lot faster, which we see in these charts. Also, finally, these results really build on the results from homework 1 of optimizing memory access, because as you can see with these charts, when we increased or decreased, the number of memory accesses, the performance, of course, went up. So block size of 2, you see the performance was drastically decreased compared to higher block sizes. And that is it for my presentation. Thank you.
Awesome. Great job. Let's thank our speakers. Rousing round of applause. Good. So let me charge through some of the follow-up material, and then we'll circle back and have a little bit of discussion. Okay, so I ran some tests too, but I went one step further and did an additional problem size. And so what I noticed is that with CBLAS, the megaflop rate continues to rise up until this problem size 1024, at which point the megaflop rate begins to actually level off. It shows as a decrease here, but It's actually starting to level off. And so we're going to talk about this. This is a performance signature that is not unfamiliar. We see this quite a bit when we start looking at trying to evaluate, is a code memory bound or is it compute bound? And this kind of signature indicates that CBLAS is transitioning from a regime here in smaller problem sizes where it's memory bound into a regime where it becomes compute bound and it just can't compute any faster. And you'll notice that at this 1024 problem size, that CBLAS is getting about 50% of peak on the Knight's Landing processor, which is pretty darn good. In contrast, my basic implementation, which is basically the same as yours, it's pretty awful. The best I got was 421 megaflops at a problem size of 128, which is only 1% of peak. And my worst is at the biggest problem size at 0.2% of the peak. And the issue here is that memory access time and the patterns, the way that memory is accessed, is what limits performance. Oops. So for the comparison of the blocked version versus CBLAS, so here we see CBLAS doing its thing, and then all the blocked versions, they kind of look similar. And this chart's kind of awful. You really can't tell much of anything. So let's try something different. So I changed to a log scale. And now here we begin to see something a little bit more interesting. So as others have reported, the block size of 2 is just awful. It does okay for a while, but then it tanks from going from 256 to 512. And then it just stays in the tank and it never recovers. The other 3 configurations have pretty similar performance across all problem sizes. The issue with the block size of 2 is that it's doing more work, copying stuff in and out of the blocks, and there's just the loops are not big enough to actually amortize the cost of doing all those memory accesses. So in a way, it's not too surprising. So if I change the plot around a little bit, I got rid of CBLAS and I dropped in the basic. And so the vertical axis is megaflops and the horizontal axis is problem size. As some of you all have reported, the basic version did pretty good, at lower problem sizes, and then it tapers off and reaches a steady state level that's not so great. In my tests, I see that the block 64 shows the best performance, and it seems to show pretty consistent performance at about 394 megaflops, 1% of peak going forward. So the blocking approach here actually helps to save you from the pitfalls of poor memory access patterns with large problem sizes. The block sizing can help, but it doesn't. It can't beat BLAS. And so let me stop here for a second and let's have a little bit of discussion about homework 2, and then I'll continue on. So, were there any surprises for you here in homework 2? Are there any questions about any of the presentations that you saw? Well, maybe not.
Professor?
Yeah, go ahead.
I have a question about the graph that you showed. Like blocked, if the block size is 16, it goes up first and then it goes down.
Okay, so, sure. Let me share that again. Hang on a second.
Sure. I think it's the last graph.
I just need to get it teed up so that we can see it. Let me put it up here so that we can all see it.
Right. So the green line.
Yeah.
It first goes up and then it goes down.
Yeah.
What is the like possible reason for that?
Yeah. So more of this blocking size is probably more friendly to the L1 cache size on that machine, right? So it's 32K of instruction and 32 kilobytes of data. And so, all other things being equal, more of the problems fitting in L1 cache and it's being accessed more from L1 cache. That's really the only difference that would make any sense here at this level. Because when we get further out, we're no longer fitting in L1 cache, and instead all of this stuff is happening out of L2 cache.
Okay.
Yeah.
Is there a way to actually find out what cache is being used at what time?
Oh, that's a wonderful question. I love that question. Yes, there is, but we're not going to talk about it today. The short answer is that there's additional performance measures that we can collect. So right now we're just collecting runtime, but we can actually ask for information about cache utilization, memory system utilization, and we're going to be doing that for some of the future assignments. Yeah, it's a great question. Okay, I'm going to charge ahead. We have a lot of material to cover. So let's see. Thanks again for the presentations. You all did a great job. Okay, so why is CBLAST so fast? Well, so, sorry, one more question. Does the result affected by how many vector processing units Core E, KNL has? So each core has 2 AVX 512 units, and the thing is that I'm not sure that if it had 8 rather than 2, would the results be any different? And so we're actually relying on the compiler to do a lot of work for us. And will the compiler actually make use of multiple vector units on the chip? And I'm not sure about that. That's a good question. I can imagine if I were handwriting assembler that I would actually look at the register set on the chip and write assembler so that it would explicitly make use of both pipelines. And I don't know if the CBLAST guys have done that or not. So I do know that the CBLAST does use handwritten assembler for some of these kernels. And I also know that they are, different kernels are used for different block sizes. And so one of the speakers made a comment about, maybe CBLAST is doing some probing or something at the beginning to figure out which configuration to use. Yeah, what I noticed is that the first time I run anything on a compute node, it's slow, and it's like I need to get the compute node's attention or something. So it may just be other system libraries that need to get loaded. I don't think there's any serious probing of the hardware, etc. But we don't know. We're speculating. If you're interested in more about matrix operations and how to squeeze out the last drop of performance, there's a couple of links that you can dig a little bit more deeply. I think one of the takeaways here is that if you can avoid having to write vector matrix code yourself, you use the one the vendor supplies because they've actually put a lot of money into it. Okay, so changing gears a little bit. So some terminology that we're going to be using today. So N is problem size. We're used to that. We're used to seeing that in homework. That's the measure of the amount of work to be done, and the amount of work to done is separate from the algorithmic complexity. So you can have an algorithm that is linear with respect to N, or sublinear, or quadratic, etc. The letter P we're going to use to refer to parallelism. And this is the number of parallel processes, and it's independent but related to how you divide the problem up, the big problem up amongst P different workers. So P is the number of parallel workers in the mix here. The word rank here is used. This comes from MPI. MPI means the message passing interface. It's the library used for doing distributed memory parallel work. In MPI parlance, a rank is one of the processing elements. It's one of these P's that we're talking about. And so often the word rank is used interchangeably with to mean a parallel process. The idea is that rank is logically independent from how it's implemented. So in other words, you can have multiple ranks map onto a physical single hardware thread, and that's an OS implementation issue. A rank is one of the parallel workers in your program. So parallel performance measures. So I love this picture of the dog sled, right? So you can look at this dog sled and you can begin to think, about speed up, right? So if I add more dogs, more huskies to the team, will the sled go faster, right? So that's a good thing to think about, right? So if you, and so how much faster can an N husky sled go compared to a sled where there's just one husky pulling it, right? So speed up is an important thing to think about. Scalability. So as you increase processors, for example, does the processing time decrease linearly with respect to the number of processors? So this is a measure of how quickly things improve. And then another measure is load balance. And so this is the degree of variance of execution time across the P ranks. So in our Husky team here, one of the Huskies might be really strong and doing more work than the others. One of the Huskies might be really weak and doing a lot less than the other Huskies. And so for this moment in time, I just want to give you a caveat. I'm oversimplifying some of these concepts and terms, so we're going to unfold these in more detail as we go on. So speed up. The idea is how much faster is a parallel code compared to a serial code. And so, speed up is a ratio of a parallel program speed to a sequential program speed. And here, T star n is the time required for the best serial algorithm on a problem size of n. And T n of P is the time required for a program that's run P-way parallel on the same problem size. And so the numerator is presumably always larger than the denominator, unless something really bad happens, right? Because as you throw more processors at the problem, the runtime should decrease. And so the speed up is the scalar measure of how well the parallel process is working in terms of actually making things run faster. And so here's a warm-up. I want to give you a couple of examples because you need to do this in homework 3. So here I have a toy problem. I have problem sizes of 100, 200, 400, and 800. My serial performance time, and I just made this up. So, if the problem size is 100, serial time's 10. Problem size is 800, the serial time is 80. So you can see a direct linear relationship for the serial program, right? So this serial program has linear complexity. It's not n squared or n cubed. And when I plot out that runtime, the serial runtime, you can see in this linear scale plot what looks like sort of a quadratic curve. If I changed it to a log scale, it would be a flat, straight line. Now, for a parallel program that runs at P-way, 4-way parallel, here's the execution time. And I've sort of made these numbers up. They're not entirely made up. I generated them according to a formula that we'll talk about in a little bit. And here, I'm seeing, a different runtime. And the only point that I'm trying to make in this plot is here I'm plotting runtime in terms of seconds. I'm not plotting megaflops. And I just wanted to give you an example of what runtime looks like. And so just looking at this runtime, you would probably say, well, the P equals 4 is performing, is certainly running faster than the serial program, but is it really running 4 times faster at all problem sizes? So that's the takeaway question. So if we change and look at speed up instead, so here I have the same problem size, the same serial size, the same serial times, the same parallel execution time, and now I've computed speed up using that formula, using this formula here, and I'm plotting out these results. And so here I've made up the data for ideal speed up. So in an ideal situation, I'm using 4 processors, and so the ideal speed up would be a speed up of 4, regardless of problem size. But that's not what I'm seeing. Instead, what I see is for a small problem size, I'm seeing a speed up of 3.5, and a problem size of 200, a little bit less, and so on and so forth. And the speed up is diminishing with increasing problem size. And so, one of the questions you might be thinking in your head is, well, why is that? And that's a good question. So let's look at a different example. Let's look at a speed up plot of something that you might see in homework 3. This is a hint. And so here I've got an open MP version of vector matrix multiply that I'm running at several different levels of concurrency, on my laptop, and I'm computing speed up for this problem. And here's what I see. I see, in blue, for 2-way parallel, I see a speed up of 2. Sorry, I'm pausing here. There's an issue here at the origin, but we'll ignore that for a second. Basically, the OpenMP 2-way parallel code is showing a speed up of about 2 for all problem sizes. It's a little bit more than 2 for some of these problem sizes, and that's not entirely unexpected. So don't worry about that. There's a explanation for that. An explanation is that you can do better than linear when you have multiple parallel processes that are actually taking advantage of cache together. And so this is one way that you can actually get super linear speed up. For the OpenMP equals 4, we see for 2048, we almost get 4-way parallel. For 4096, a little bit closer to 4-way parallel. And then for the higher problem size, we get a little bit more than 4-way parallel. For the 8-way parallel code, at the smaller problem size, only 3-way parallel. But then as we increase the problem size, the speed up, begins to approach. It gets closer to 8, but it's never quite going to get there. So again, the problem here is that at the origin is that this shows a speed up of 1. And what I've done is I've divided by the wrong number here in producing this chart. So this chart has an error in it. What I would expect for your chart is that for the smaller problem size, that OpenMP 2-way parallel is going to be about twice as fast as the serial code, and so this origin point maybe should be about right here. I'll go have a look at that later. So what do these speed up plots tell us? So for a given problem size, the speed up metric shows how much faster you're going, how much faster you're able to solve the problem if you're using P ranks rather than a serial implementation. So question for you, why is the maximum possible speed up equal to P? So if I have 2 ranks and I get a 2-way, a speed up of 2, that means I'm running twice as fast with a 2-way parallel job compared to a 1-way parallel job. So in principle, I can't go any faster than that. But if I do, it means that there's some, super linear effects having to do with caching or something that are not accounted for by, the equations. that are pretty well established for computing speed up. It's not a cause for concern, but you need to pay close attention to why and do more investigation to figure that out. What does it mean if the speed up is less than p? It means that there's a problem that we're going to talk about in a few minutes. So when we talk about scaling, there's two kinds of scaling. One of them is strong scaling. And so strong scaling means that we hold the problem size constant. We have a problem of size n, and it takes t seconds to execute to complete. But if we can if we can run it in parallel, then we can take that size n problem and solve the same problem in t divided by k seconds. This person uses k as the p, as the measure of concurrency. So that's what strong scaling refers to. We keep the problem size constant and throw more processors at it to get a faster time to solution. So when in an ideal situation, if you have two processors, then the code would complete in 1/2 the time of the serial code. If you have 8 processors, it would complete in 1/8 the time of the serial code, etc. And things don't often work out that way. And the scaling factor is reduced by some awful thing that we'll call f. And you might be thinking, well, what is f? And the answer is it comes from Amdahl's law. And so Amdahl's law says basically that for any given program, only a portion of it can actually be made to run in parallel, and the rest is run in serial. And as a result, there's a limit to what you can actually achieve in terms of strong scaling. And so, according to Amdahl's formulation, f is the portion of the program that must be serial. And so that f is what's tanking us in the previous examples. 1 minus f is the portion of the program that can actually be run in parallel. And so the limit to scaling, strong scaling, for any given n and p is given by this formula here. And what this says is, remember s is speed up, the scaling, speed up. And so when f is big, the amount of the serial code is big, and f ranges from 0 to 1. When f is big, this speed up is going to approach 1. It's going to be limited to 1. It's not going to climb any larger than that. However, when f is small, then this part of the denominator is going to dominate, and it's going to be 1 minus 0, let's say, so 1 over p in the denominator, and the scaling level will approach p. So that's what this says. Amdahl's law says that there's only a portion of the code can be made parallel. The serial portion is f, the parallel portion is 1 minus f, and this serial portion limits us in terms of our scaling. This effect, yeah.
What type of code typically falls into that f portion?
So you remember last time we talked about doing reductions in OpenMP, right? So there was a portion of that vector dot product that could be done in parallel, but then there was a portion that had to be done in serial. And so, you can divide the vector up into chunks and do, element-wise multiplication, but then, gathering all of those products together is inherently a serial process. And so that's one example. So the effect of f becomes amplified at increasing p. And basically the idea is that as p gets larger, we're spending more and more of the total time doing that serial work and less of the time doing parallel work. And so if it's not obvious, one of the objectives is to minimize the amount of time that we're doing serial work when we design our parallel codes. And so here's some examples of how f can affect speed up at varying levels. And so if f equals 0.5 says half the code is serial and half is parallel. And as a result, the asymptotic limit of speed up in that code is 2, right? It's never going to be faster than twice as fast, regardless of how many cores you throw at it. And you can see the trend here at 10% scaling. At some point, you're only at this point here, speed up of 5 when you're throwing 10 cores at it when only 10% of your code is serial. And this has a pretty profound effect on your code. So over time, as you begin to look at a bunch of these performance charts, you'll begin to see characteristics of, the impact of, serial code in parallel code performance analysis. Right? So this is a very common sort of thing. Okay, so strong scaling is where we hold n constant and increase p to reduce the time to solution. Weak scaling, as p increases, n also increases. And this is actually a key idea for using these large HPC machines to solve larger problems. And some examples are higher res climate models where instead of having 1 degree grid cells, you have like 1/10 of a degree grid cells where you need way more memory that can fit on any one node. You actually need all half a petabyte or whatever of memory that's on the machine to actually solve the problem. Weak scaling. So Amdahl was talking about strong scaling stuff back in the late 60s. And this guy, John Gustafson, introduced the idea of weak scaling back in the late 80s. And so the idea basically says, so Amdahl has a law, Gustafson, not to be outdone, has his own law too. And basically it says that as N and P get larger, N and P get larger, that the impact of the amount of serial work that you have to do becomes less and less impactful on the code. So Amdahl's law was different. Amdahl said that as P gets bigger, holding N constant, that F is going to kill you. And here, Gustafson says that he says S rather than F. As N and P get bigger, the impact of S becomes less and less apparent. It's not as impactful as it is with Amdahl. And so here's an example. If you have if we decide that, or if we discover that F equals 5% of the code is serial, and we have a 64P machine, then the scaled speed up, that's what they refer to it as. You can crunch the numbers here and come out with 60.85 as scaled speed up, which is pretty good for 64-way parallel code. So this is what I just said, yeah. So there's a different measure that we might want to think about for weak scaling, and that's computational rate. And so basically it's the ratio of problem size to running time. So in the numerator here we have the problem size, and in the denominator we have the time to solution for a given problem size with a given number of processors. And so this gives us a rate of computation with respect to problem size. And so this is a better way of measuring performance. It's a little bit more normalized from concurrency level to concurrency level. Okay. I have more. We're going to talk about additional metrics another time, but they build on this computational rate. So for homework 3, you're doing speed up, the strong scaling speed up, because that's what you're doing. You're holding, even though you're running at different problem sizes, you're doing comparison of runtime at different levels of concurrency. So you're using the speed up formula from strong scaling that we presented here a minute ago. So there's another performance metric that's called load balance. And the basic idea is that, if all is well, as you divide up your work, each of the threads, each of the P ranks is going to take about the same amount of time to finish. And so in this example, each of these threads, these 4 threads, executes in about the same amount of time. There's a little bit of variation, but that's okay. In contrast, if there's a lot of, load imbalance, then what we see in this example is that thread 3 takes 2.5 times as long as thread 1, and so this is actually pretty bad. This program finishes in 19.15 milliseconds. This program doesn't finish until 25,000 milliseconds, 19,000 milliseconds, 25,000 milliseconds, even though the first thread finished at 10 milliseconds. You got to wait for the last guy to finish before the program is actually over. So what are some sources of load imbalance? Well, so one is the uneven distribution of work across the set of P ranks. Another is data dependency. And so a lot of problems are data dependent. The number of computations required is a function of the data that you give it, right? So all of these matrix multiplies and vector matrix multiplies, you can put anything in there and it takes the same amount of time. But if you're like, computing prime numbers or something, if you're trying to compute a big prime number, it's a heck of a lot more expensive than it is to compute a small prime number. And so that's a good example of a problem dependency. There may be some system fluctuations as well, like one of the nodes may have an OS hiccup or something that would cause load imbalance, even if you perfectly distributed the work and were able to account for potential work variations as a function of input data. So this idea of measuring, predicting, remedying load balance, this is an area of active research. There's tons of papers on this. It's a hard problem. How do you quantify it? Well, so you measure the runtime, for example, on all the P's, and then you compute a statistical measure like standard deviation to get a measure of what's the spread in runtimes. And so again, this is a big research area. How do you visualize load imbalance? Well, so this is a pretty interesting chart here. We have a bunch of threads. We're looking at performance data for a bunch of threads, and for each thread, we see a bunch of different information. We see information about time spent in a solver, so physics solver, maybe a CFD solver or something. That's shown in green. Gray shows time spent in some chemistry solver, and red shows time spent waiting. Oh my God. And so let's look at this for a second. This is actually really interesting. So let's look at thread, I don't know, it's like 36 or something. So we see a lot of load imbalance here in the chemistry computation, right? So all the green stuff looks pretty similar. But this chemistry stuff, this got some pretty serious load imbalance. There's a few ranks that have a lot more runtime than most of the others. And so none of the program can proceed past this point until, these guys finish with their chemistry calculations, right? You can see that all the other guys are waiting, right? That's time just wasted. So this is one way to visualize load imbalance. And most of the examples that I've seen involve, these stacked histogram or stacked, timeline charts. In this example, it's not too bad. There's 30 or 40 threads, but you can imagine how crazy things would be if you have a million way concurrent program. And that poses some real challenges, both in terms of collecting and managing all of that performance data, as well as visualizing it. Okay, so that's it for the new material. My intention was to introduce you to the scaling measure and making some charts with it, and to give you some examples. And I gave you a busted example. I apologize for that. I will fix it before I upload the